And we still have another 15 minutes or so, so I'm going to go ahead and start 6.2. All right, so in 6.2, we already talked about normal distributions. The handout here says there's many normal distributions, all distinguished by their means and their standard deviations. All of the probability distributions are normal with different means and standard deviations. But they all come from the same formula and they all have the same total area underneath of 1. Okay, so you can see that the skinnier ones have to be taller so that the total area is 1. The wide ones can be very low. They're so wide that the bell has to go to a lower height so that the total area is still 1. Okay, important facts about normal distributions. The mean and the median are equal. Half the values are below the mean and half are above the mean. The normal curve is bell-shaped and symmetric with respect to the mean. The area under the normal curve is 1. Normal curves extend endlessly in both directions, but are very nearly 0 for values more than around 4 standard deviations above or below the mean. The normal curve changes its curvature from downward to upward at 1 standard deviation above or below the mean. So I want to show you what I mean there. Here's a downward curve. Okay, and then upward on either side of that middle area. Okay, this part in green is an upward curve. It's like a right side up bowl. And on the left also upward. We're hearing that. Okay, so between these downward and upward curves, you have inflection points. This occurs at 1 standard deviation above the mean. So right here in the middle is the mean. Okay, this is 1 standard deviation above the mean. This is the mean plus 1 standard deviation. Okay, so at 1 standard deviation above the mean, you have the inflection. Also 1 standard deviation below the mean, you've got another inflection. Okay, now it's going to ask us what the z-scores are. I wonder if I have to do this here. I shouldn't have written this. Now z-score is the number of standard deviations that a value is from the mean. Okay, so z-score is the number of standard deviations a value is from the mean. All right, so unfortunately I shouldn't have written this garbage here. What it's asking me to do is put how many standard deviations the value is from the mean. So in the middle here, I think I'll write this vertically, z is 0. Okay, now that's hard to read also, I don't like that. So I'll just write it really small. So z is 0 there. Now when you go 1 standard deviation above the mean, that's a z-score of 1. 2 standard deviations, that's mu plus 2 standard deviations, z is 2, and so on. Don't forget, when you go below the mean, the z-scores become negative. So this is 1 standard deviation below the mean on the left. So below the mean means negative. Z is -1, then -2, and so on. Okay, so I got that covered. It does ask for the z-score formula here, so let's squeeze this in. So the formula for z is x minus mu over sigma. Like that. And I think we're good there. Any questions? So the inflections occur where z is 1 and z is -1. Now it's asking what's the mean of the z-scores? Well, you can see the z-scores on here. Anybody want to say what the mean of z-scores is? The z-scores are attached to this bell-shaped distribution. The probabilities are on the bell-shaped distribution, and in the middle of all the probabilities, the mean where z is 0. So the mean of z-scores is 0. Now the standard deviation of z-scores. What? Standard deviation of z-scores. Look at the picture. The inflection is 1 standard deviation above the mean. The mean is 0 for z. How far up with z is the inflection point? Somebody typed a 1. Thanks, Wenjing. The standard deviation of z is 1. That's correct. All right, so the important fact down here, for any population of z-scores, the mean is, I'll use a mu with a little z subscript, which means that the mean of z-scores is 0. And the standard deviation will do a sigma with a little z subscript. Standard deviation of z-scores is 1. The empirical rule we've talked about before. It applies to normal populations, and then the graphical representation is here. 68% of values are within 1 standard deviation from the mean. 95% are within 2 standard deviations, and 99.7 are within 3 standard deviations. Okay, any questions here? That's an old fact from chapter 2, I think. Okay. Now it says adult men's heights are normally distributed with a mean of 69 and a standard deviation of 3. The graphic below represents the distribution. So the 69 would go in the middle. Okay. It says the tick marks are 1 standard deviation apart down below. Standard deviation is 3, so that means I would add 3 to get to 72. Okay, this is the inflection right here. 1 standard deviation above the mean. And then the other one, of course, is on the other side. Then 75, then 78. That's adding a standard deviation each time. Okay, then subtracting a standard deviation, there's a 66, then 63, the standard deviation is 3, remember. And then subtracting 3 again takes you down to 60. That's 3 standard deviations below the mean. Okay, any questions? I don't see anything. That 68% here is divided into 2 down here. So what are those individually? Yep. Now we'll do 0.34. Any questions? All right, now, if you want to find these 2 gray areas that I'm going to highlight here with a circle, this one and this one, okay? This whole region is 95%. If you subtract out the 68%, you would get that light gray area. So take 0.95, subtract 0.68, and then divide it by 2 because the region is divided by 2 into 2 gray parts. And what do you get? Yeah, 13.5%, which we'll write as 0.135 on each side. You're not going to do this on a test. It's just sort of trying to help you see the logic of how we can really figure out probability under bell curves based on empirical. Okay, we got a couple more tails to figure out. So this time, we want to take the 3 standard deviation range, which is the 99.7 range, and subtract out the 95% range, and divide that by 2 to get these dark area, these dark gray regions. So 0.997 minus 0.95, and then divide that by 2. And again, we're seeing an answer. Sorry, question?
2.35.
Yeah, thank you. And I'll write it in decimal, 0.0235 on each side. And you have to take the whole area, which is 1, and subtract the 99.7. So you would do 1 minus 0.997 to get these 2 little slivers. Divided by 2, and you'll get each individual sliver. And I think you'll see that's 0.0025 on each side. Okay, so that's kind of slicing and dicing a probability distribution up. I think we can squeeze this next part in. This is for men's heights here. If I copy these probabilities, not the heights, but the probabilities over, these probabilities apply to any normal distribution, okay? So these are the same probabilities for any of these bell curves. So I'm just sort of saying, okay, well, that applies here as well. Okay, but this one's a distribution of z-scores. Okay, remember the z-scores, if this distribution is z, then z goes from 0 in the middle, that's the mean, and the standard deviation of z-scores is 1, we said. So you can just go 1, 2, 3 like that. and negatives on the left. And that's what's called the standard normal distribution. And basically the idea is, this is called standardizing when you use the standard normal distribution. You take any normal distribution and you compute z-scores, and it always looks like this when you're done. Okay, so any normal distribution can be transformed into a standard normal distribution by taking z-scores. And then this table down below gives areas under that curve. So I'll show you how to use that next week. And for now, we're going to stop and get ourselves ready for the exam. So we want to be able to find the probabilities for any region under the standard normal distribution. As I say, the standard normal distribution has a mean of 0 and a standard deviation of 1. So if you go back, I think at some point we gave the density function for the normal distribution. The density function is just the name of the curve that sort of outlines the distribution. So let me show you the density function for a normal distribution. Okay, we talked about that in the first lesson in this chapter. But with the normal distribution, the mean is 0. Okay, so the mean sort of vanishes from the equation. And the standard deviation is 1. So the standard deviation becomes 1. And here as well. So basically, that's kind of how the thing plays out. And we don't call the variable x, we call it z. So I'm going to change that real quick here and write it down on the current lesson. Oops, right here. So the density function for the standard normal, this is the distribution of z-scores. Y equals e to the negative 1/2 z-square. I would normally have a sigma times the square root of 2 pi, but sigma is 1, so we'll just put the square root of 2 pi down there. And so when we do areas under that we are doing probabilities for that distribution, standard normal. Okay, so I'll go ahead and read this down here. It says, to find probabilities for a normally distributed variable x, we compute z-scores, that's standardizing, and then look up the z-scores on table A1. This table gives areas to the left of any z-score, rounded to the nearest hundredth. Okay, areas to the left only. All right, so let's look at some of the problems on the following page. It says, find the probability that z is less than 1.29. Z is just a random z-score. So the way the table works is you're going to look up your z-score this way, just 1.2, so that goes out to the 10th place. And then the 100th place has to be this way, 0.09. Now those add to 1.29. So you got it as 1.2 plus 0.09 makes 1.29. And then when you go in to the sort of the intersection of the row and column for those headers, that should be the probability. So let's go back up to the table here, which you may notice has a negative z-score side and a positive z-score side. We're doing 1.29, so let me see if I can find that. Okay, any questions about how that works? So again, this is the area to the left. Only areas to the left here. So if you need an area to the right, you're going to have to use the rule of complements, which is because left is the opposite of right. Anyway, it's 0.9015. Let's go and put that in as our answer. You can interrupt and ask a question anytime, you guys. I'm not seeing any. Okay, so let's do the next one. Z is less than or equal to negative 2.53. The or equal here has no bearing. The equal part is an infinitely thin line that has no area, so it doesn't affect the area, which is the probability. Let's just look up negative 2.53. This one's negative. On the left side of the table. So negative 2.5012 right there. Okay, so any questions about this one? That's 0.0057. And again, it's the negative 2.5 and the negative 0.03 that add up to negative 2.53. Okay, looking for questions. Okay, next one. This one's a greater than. Okay, the table only does less than. So for greater than, we have to use rule of complements. Okay, so the rule of complements says the probability of the opposite event is 1 minus the probability of the event. Okay, so right off the bat, I know I'm going to do 1 minus on this one. And let's look up the 1.67. So 1.6 out to 0.07 here. So I'm seeing a 0.9525 there. Why? Okay, Susan's asked a question. You're referring to the last one, so let me get back to that. But anyway, 0.9525 real quick for this one. 1.67, oops. 9525. And then could somebody just subtract that for me? It's like 0.04 something. I think now, okay, for 0.0475, thank you so much, William and Wendy. Okay, so that's the answer to the question. Now, Susan's asking a question real quick about the 3 in the second decimal place here. So on the previous problem, the the tenths place is the 5. Okay, so with the tenths, you're going to look up a negative 2.5, and the hundredths is the 3. You have to break that up as negative 2.5 and negative 0.03. Okay, all of the z-scores are going to be rounded to 2 places after the decimal, because the table can only take you to the nearest hundredths. So remember, the negative 2.5 is here on the table, and the 0.03, the negative, really, 0.03, those are part of the z-score. Now the probabilities are to 4 places after the decimal. Okay, but the z-scores have to be rounded to 2 places just because that's kind of the limitation of the table. Susan, does that make any sense? You see the negative, okay, you see that negative 2.5 and then the 3 up above, making the z-score. Okay. But on this one, again, this table only does the areas to the left. Okay, so when you're asked for an area to the right, you have to use a rule of complements because those are opposites. And when we do the opposite, that's an A, like the opposite of A is an A with a bar over it. And you have to do 1 minus the probability of A for that. Okay, so that's the gist of that one. And then to be in between two numbers, this is the most, and it's not hard, you have to look up 2 numbers now. So you're going to look up the 2.15, and maybe I can draw a picture of this one. So, so you're going to look up a 2.15 and look up a 3.11. Okay, and remember these give areas to the left. So when you look up the 2.15, you're getting everything to the left of that. And that's not what you want. You want the area between 3.11 and 2.15. So if you look up the 3.11, I'm going to crosshatch this. Okay, so you're getting all of this. Okay, and what you want is, what I'm going to highlight is the green area here. This, what I'm highlighting in green is what you want. Okay. So I would say that, how about this? The green area, what you want, is equal to the blue crosshatched area that I did, minus the red area. Okay, you have to subtract those. So you got a couple things to look up. So with the 3.11, you can do it first or second. I'm doing the bigger one first because that's the one you need to subtract. So for your z-score, you go down to 3.1 and then out to 0.01 like that. And let's look that up above. 3.1 and then 0.01. A little messier here. Way down below, 3.11. Okay, so that one says 0.9991. So we're almost to the point where we've captured all the curve. Remember, the total area is 1. So we've almost gotten to 1 here. Once you're at 4, you're basically capturing the full curve. We're at 3.1. Any questions? 0.9991. Okay, and then we also have to look up the 2.15. Okay, so let's find that one. I think I'll switch colors here. So this is a little easier. 2.1 is here. And here's a 5. So I'm seeing a 0.9842. Okay, any questions about that? 9842. Okay, so the 9991 is sort of my blue cross-hatched area. So let's see if I can be creative here. I'm kind of doing blue crosshatches. That's not very good. Across the 9991. And then the 9842 is the red highlighted region. So, oops. Highlight that in red. Okay, and we'll just subtract those. So take the big number always, 0.9991 minus the small number, 0.9842. You always do big minus small when you subtract probabilities because you don't want a negative probability. That is not something we ever understand or talk about. All right, so has anybody got that? 0149, thank you so much, Wendy. I guess I should take a little bit of space here. And for those of you who bought the calculator that is recommended, I'm going to show you how to do this on that. Okay, so this is the TI. There's not a lot of calculators out there that do normal curve probabilities. This is a relatively inexpensive calculator that does. So let me just show you. You might like this better, and you're welcome to use it. You don't have to use the tables. The tables are a pain. TI-36X Pro. So you do second, then data, and you press the right arrow to highlight the distribution menu. I think the buttons are around. Second, data, right arrow, distribution's a menu choice, and then you're picking a menu item 2. Is it item 2? I think so. 2 is normal CDF. Okay, and then you're going to want to put in the normal distributions mean. I'll just remind you, for the standard normal distribution of z-scores, we said that is 0. Okay, and the standard deviation is sigma, and that should be 1 for the standard normal distribution. And then it asks for a lower bound. Okay, so that's the left endpoint. And then the upper bound that's your right endpoint. Okay, and then maybe a little note here. If there's no lower bound, meaning it goes forever to the left, You would use negative infinity, which is effectively a really big negative number. I'll do negative 999. Remembering that the curve basically zeroes out when you get to about 4 standard deviations from the mean. So this should cover that. If there's no upper bound, so it goes to positive infinity, then use a positive 999. Okay. So let me show you that real quick. And I think what I'll do is I'll repeat all of these. So let me just get to my camera here. I hope this works. Zoom has really been having a hard time. I think it's just for Zoom. That's all I can say. It's been through a lot. I heard the CEO of Zoom being interviewed on NPR yesterday. I think it was yesterday. And he was, boy, pretty cheerful guy. Trying to look at the positives. But Zoom's been getting a lot of bad press, which I kind of feel bad for them. They didn't sign up for the coronavirus, you know what I mean? Anyway, so I said second, data, and distribution is on the right. Okay. And we're doing the normal cumulative distribution. So cumulative distributions are how areas accumulate under curves. So that computes the area under the curve. I told you how the probability density function is just the curve itself. So when you execute normal PDF, that's the probability density function. It just gives the height of the curve at a point. That's not what you want. You want the area under the curve, which is the cumulation of area, CDF, cumulative distribution function. So you pick item 2. The mean and standard deviation default to 0 and 1 as they should for the standard normal distribution. You should enter through that. And it asks for a lower bound and an upper bound. Now I have to go back because I don't have this printed anywhere. So real quick in Notability on the first one, well, let's do the last one. So the lower bound on this last one was 2.15. The upper bound was 3.11. See if my camera's still in focus. Probably not. Okay, 2.15 and 3.11. Okay. And you hit calculate, and so 0.0148. And I'm hoping we weren't too far from that. We got 0.149. Okay, and the 0.148 is actually more precise. Okay, the tables are pretty good. You have multiple roundings that happen with the table. You're working with two rounded numbers, and the calculator is not rounding until it gets to like the 16th digit or something like that. So the calculator is just right. Okay. That's pretty slick. If we go to one of these earlier problems, like negative 2.53, that one goes forever to the left. And if I let me draw a picture of that. Actually, let's do the first one. Z is less than 2.19, so a little picture might help. So actually it's 1.29. These are z-scores. I'm asking for the area to the left, and it goes forever to the left. So there's no lower bound, and we'll use negative infinity, which for our purposes is negative 999. Okay. So I just point off like this and say that it goes off to negative infinity. Okay. Okay, so back to the calculator. The lower bound will be negative infinity on this one. So let's see, focus, find it and focus. Okay, this is the last problem that's still on here. So I can go into solve again, and it'll ask me for the mean and standard deviation. Those cannot change. Oh, dang it, I forget what it is. 1.29, got it. Gotta refocus. 1.29. There was no lower bound, so we just used negative 999. Upper bound was 1.29. Okay, and so this is coming out 9015. And I think, what do we get? 9015. So if there's only one value involved, then there's only one rounding involved. So you get pretty similar to what the table gives. Okay. So no lower bound, we use negative 999. Okay. And then let's do this one here with the 1.67. That one had no upper bound. So that one you use infinity for the upper bound. 1.67, I'm focusing. There we go. So I'm going to solve again. Enter through all that. Good. The lower bound was 1.67 and there's no upper bound. So you can put in just a huge number here, as many nines as you like. And so 0.0475 is how that should be rounded. Okay, 0.0475, I guess. And that's what we got. Does it work with the TI-30 Nicholas Corona? No, it does not. This is the TI-36X Pro, and you know, Pro's got to mean something, right? So I guess you're just not a pro with the TI-30. No, it's the, I'm sorry, that was not nice. I feel bad. Okay, any questions? There are some Casio calculators that I found. If you've got a fancy Casio, some of those have the normal distribution, but it's pretty rare. Any questions? All right, so that kind of summarizes everything you need with that TI-36 calculator that I was recommending. Otherwise, I don't want to spend much more time on the calculator, so let's fly through it. This is just a summary. For a probability of Z less than A, you just look up Z equals A on table A1, which is the one we're using up above. And you just give the area. Okay, then for probability of Z greater than A, you look up Z equals A on table A1. And give 1 minus the area on the table. That's for the greater than problems. And for the in-between problems, you look at both of these values. You look at Z equals A and Z equals B in table A1. And oops, just the larger area minus the smaller area. Okay. Any questions? So that's just kind of a summary of what we did. Any questions? Okay, now it says let's do the reverse problem. Find the z-score that's associated with a right tail of 0.025. Wow. It says the right tail is 0.025. like that. Now our table only gives areas to the left, so we need the area to the left. And so that would just be rule of complements, remember, 1 minus the probability for the opposite probability. So this would be 1 minus 0.025. And I think that will give you a 0.975. I'm going to add a 0 to that because the table all has 4 digits everywhere. And then if you look at table A1, you have the area, not the z-score. Okay. We're trying to find the z-score, so I'm putting a big question mark here. Okay, so we're looking, and if you see something close, and I think this one's actually in the table, there's a 0.4, sorry, 9750 in the table. Now let's see. Clean out some of this here. So just kind of have to search. It's a little tedious because it's dense with numbers. There it is, right there. So just circled it. Hope you can see that. And it's corresponding to 1.96. Okay, does that make sense? We're doing the problem in reverse here. We're starting with a probability and going back to the z-score, which will actually be an important tool for us. But we'll have a better way to look it up later. But right now, this is how you're doing it. Okay, so let's just go back here. 9750 came out as 1.96. You just find the closest one to 0.9. 1.96. Just find the closest thing you can to the probability they give you, 0.9750. So that tells us that z is 1.96, and that's the mystery z-score. Okay, so keep an eye open. There will be some problems like that in 6.2. Okay, any questions?